Hello everyone, welcome to the video. Today we are going to solve the problem Pythagorean triplet. In this problem, we are given an array of integers and we have to see if there exists a triplet such that a square plus b square is equal to c square. If there exists such a triplet, we have to return true, otherwise we have to return false. For example, in this array 3, 2, 4, 6, 5, the triplet 3, 4, 5 satisfies this relation. Hence, we have to return true. This is a fairly simple problem, but while solving this problem, we will discuss multiple approaches which are very common and which we can use in many other problems. Then, finally, we will code our solution through one of these approaches. We discuss the questions of data structures and algorithms on this channel in simplest words with fundamental approach. If you are new to this channel, please subscribe. Let's start. To begin with, let us first note down the key things given in the question. We are given an array of n integers. The condition that we have to satisfy is a square plus b square is equal to c square, and we have to return true or false. So if we consider an example 3, 2, 4, 6, 5, here 3 square plus 4 square is equal to 5 square, and hence we have to return true. So if we consider our solution as a black box, the input that we are getting is an array of size n and we have to return a boolean. So what will our function signature look like? Our function signature will look like this. Let us see what is the simplest way in which we can approach this problem. We are given an array and the condition that we have to satisfy is this. So the simplest way is that we run 3 loops. We fix A, B and C as per the 3 loops, and then we check condition a square plus b square is equal to c square. If we see that the condition is satisfied, we return true, and if after all the iterations the condition is not satisfied, we return false. How will the 3 loops run? We will fix I, then we will fix j, and then we will fix k. Then k will move from here to here. Once k reaches the end, we will shift j one place ahead, and again k will move till end, and so on. And once j also reaches the end, we will start shifting I from one place ahead, and similarly this loops will continue. Now what will be the time complexity here? For every I, j is traversing n places. Similarly, for every j, k is also traversing big O of n places. Therefore, the total time complexity will be big O of n cube. Now, this is obviously not efficient. So, let us try to see if we can find an efficient approach for this problem. Previous solution had time complexity of big O of n cube because of 3 loops. Let us try to eliminate the third loop from the previous solution. Let us say we have 2 loops and we can fix a and b. Now with a and b we can calculate a square plus b square. The only task that now remains is to check whether there exists an element in this array whose square's value is equal to this, and which data structure allows us to check the existence of something in most efficient manner. It is map or set. So what will our approach look like? We will first declare a set, then we will loop over this array, and for every element we will square it and put it in the set. Then we will run 2 loops fixing a and b. We will find the value a square plus b square, and we will check the existence of this value in the set. If this value exists, then we will return true, otherwise we will return false. What will be the time complexity of this algorithm? It will be now big O of n square because we are running only 2 loops, 2 nested loops. But what will be the space complexity here? The space complexity will be big O of n because we are now using a set. This is a very common technique that we can use in multiple problems. Whenever we have to check existence or non-existence of something, we can use the data structure map or set, because it will return that in big O of 1 time. Before moving to our approach 3, let us first try to see what was the exact inefficiency in our first solution. In our first solution, we were considering all possible triplets and we were checking this condition for it. But is it really needed to check all possible triplets? Let's see. Let's say we sort this array. Now this becomes 2, 3, 4, 5, 6. And let's say we are checking this I, j and k. Now 2 square plus 5 square is definitely less than 6 square. Now, does it make sense to check the combinations of 2 and 3 whether it is equal to 36 and 2 and 4 whether it is equal to 36? No, right? Because all these numbers are lesser than 5, and when 2 square plus 5 square cannot reach 36, obviously any combination of these numbers with 2 will also not be able to reach 36. We will make use of this inefficiency in our approach 3. So in approach 3, we have now sorted the array. We have now fixed C, and now our aim is to find A and B such that this condition is satisfied. In approach 2, we had fixed A and B and we were finding whether there exists a C or not. In approach 3, we are doing the opposite. So let's see if we can find A and B. So with this C, we start with the two extremes of the remaining array. Let us say our candidate A and B are 2 and 5. Now, what will be the A square plus B square? It is 4 plus 5, 4 plus 25, which is 29. Now 29 is less than 36. So do we know that which pointer should we progress? We should obviously progress I, because we have to increment this value to reach 36. So with 3 square plus 5 square, this will become 9 plus 25, which is 34. This sum is still lesser than 36. So we should further progress I. Now 4 square plus 5 square becomes 41. Now this becomes greater than 36. Now it is not possible that any element, if there were any element further than I, to make the sum equal to this. So we now have the new C at a previous element, which is now 5, and now new C square is 25. Now let's see if we can find A and B from the remaining array. Again, we start from the two extremes, 2 and 4. Okay, now what will be A square plus B square? 4 plus 16, 20. Now this 20 is less than 25. So we should progress I. Now we progressed I, and now 3 and 4. Now 9 plus 16 becomes 25, which is what is our C square, and hence we can return true. So let's make a few observations of what we did. First thing is that we are running a loop, and in every iteration we are fixing a C. Second thing is, once C is fixed and we are trying to find the A and B, we don't have to run two nested loops, because when we start from the two extremes in the sorted array, we know that only one pointer has to move forward, and we can determine whether I has to move or whether J has to move based on what is the current sum of these elements, of the squares of these elements, and what is the required sum. So what will our approach look like? We are first sorting the array, then we are running a loop from right to left, and in every iteration we are fixing a C. Then for this C, while trying to find A and B, we start with I and J at the two extremes of the remaining array, and we loop till I is less than J. In every iteration, what all do we have? We have A square, B square, and therefore we can calculate A square plus B square. Now, if this is lesser than C square, then we have to increase I for the next iteration. If it is greater than C square, that means we have to decrease J. And if it is equal, then we have to return true. If we were able to return true, while looping here, great. Otherwise, we have to return false. What will be the time complexity here? The sorting will take big O of n log n, and these two loops will take big O of n square. Therefore, the overall time complexity becomes big O of n square, while the space complexity becomes big O of 1, because we are not using any extra space here. So this is better than our previous basically approach to solution. This is also a very common technique where we sort the elements and then we use the meet in the middle approach. This we can apply whenever A and B, or basically any two elements of the array, need to reach a particular value. The approaches that we discussed so far all have their time complexity and space complexity dependent on n, big O of n square, big O of n cube, and so on. Now consider this situation. Consider that our array size is huge, which makes the time complexity and space complexity go very high. Our array size is huge, but the number of distinct elements is not that huge. Let's say with even 3, 4, 5, only 3 distinct elements, we have an array size of 5000. In that case, our time complexity and space complexity will be very expensive. So is there a way, or is there an approach that will be effective or efficient for such kind of scenarios to solve it in lesser time and lesser space? Let's see. One thing is for sure, that we don't want to iterate over this array in 2 loops, which result in time complexity of big O of n square. So what can we do? We can iterate over some different array which only has the distinct elements. Okay, so what can we do to get that array? We can just put all these elements into a set. That will ensure that the set only has distinct elements, and then we convert that set to list, and then we apply our previous approaches to the new list. This is what our approach would look like. Now this list only has the distinct elements, so its size is much lesser than the original size, and we will apply approaches on this list, so overall time complexity and space complexity will be lesser. Another similar way is that we find what is the maximum value in the given array, and then we declare a new array of size maximum plus 1. Now we iterate over the original array and mark the presence of the element in this array. Note that we have to traverse the original array at least once, whether in this solution or even in this solution, because otherwise how will we know that what all elements are present? Okay, so how will we mark the presence of these elements in this new array? Since we have to deal with squares, we can initialize this array with 0, and then as we see the element, let's say we saw element 3, then we go ahead at index 3 and we mark its value as 9, 3 square. Similarly, when we see 4, we can go ahead and we mark 4 square, 16. Similarly, if it would, I have drawn the lesser array here. So similarly for 5's presence, we would mark 25 in the index that is marked 5. So other remaining indices will have 0. So that is how we have marked the presence of all these elements. Now, since we don't want to iterate over this array, we will iterate over this array whose size is dictated by the maximum value. And we will run our approach 2, where we used to fix a and b in an iteration, and we used to look for a square plus b square, whether this value is present or not. So what will be the valid a and b that we can fix in this array, where hash of a and hash of b, if we call this array hash, is greater than 0. So we fix a and b in one iteration, we get the a square plus b square, then we calculate square root, and then we can just simply check if hash of index, which is denoted by square root, is positive. If this was positive, that means square root would have been present in the original array, and that is why its value became greater than 0. While this approach looks good, but there is a catch. The square root that we calculate here, this we need to see if this is a perfect square. Why? Because while the square root of 25 is 5, but similarly, if we do the square root of 29 and store that in integer in Java, that will also come to be 5. But we don't want that. If a square plus b square is equal to 29, let's say hypothetically, if a square plus b square comes to be 29, then if we can compute the square root as 25, if we compute the square root as 5, and then we cannot say that hey, this triplet is present, right? So we need to check here whether this square is perfect. A square plus b square's value is a perfect square. Now how do we check whether something is a perfect square? That is very simple. We can just check if this square root multiplied by itself actually results in a square plus b square, that value that we calculated here. For example, if a and b were 4 and 5, then this a square plus b square would have been 41. If we compute its square root and store that in integer, it will come down to 6. But now if we do 6 into 6, it comes to 36 and not 41. Therefore, we can conclude that this was not a perfect square. And if this is not a perfect square, its value could not have been in the original array, because original array is made up of only integers. What will be the time complexity and space complexity of this approach? Time complexity of this approach will be big O of max square, because we are running two nested loops in this array whose size is dictated by maximum. And space complexity will also be big O of max, because the size of this array is dictated by the maximum. Now, this is also a very common technique where we are basically using array indices as map keys. Basically, this hash of square root, we are trying to check whether it exists or not. We are able to check this very quickly because we can directly go to this index and see what its value is, whether it is 0 or something greater than 0. Therefore, array indices here are acting as map keys. Let us now see the working code for the last approach that we discussed. You can also find the link to this code in the description. First of all, we find the maximum element in the array. Then we declare a new array of the size maximum element plus 1. We first fill this new array with zeros. Then we have to mark the presence of the elements present in the original array. For that, we iterate over the original array, and for every element, we fill this new array with its square value at the index of the element. For example, if the element here was 3, we go to index 3 and we fill the value. We go to index 3 for this array and we fill the value 9 here. We will see this method once we complete the main method. Then here we declare a few variables. Then we iterate over this array, the new array that we have declared, and we fix a and b using two pointers I and j. Now, those pointers are only valid, a and b are only valid if hash of I and hash of j is greater than 0. Why? Because if they are equal to 0, that means the original array did not contain the values I and j at all, right? So once we find such a and b, we get their squares and we calculate the value candidate c square. Now we have to find the square root. But we also need to take care of the square root being perfect. So we call a method get square root if perfect, that takes a value and it returns the square root if this was a perfect square, like 25. But it returns -1 if this was not a perfect square, like 41. So if this was not -1, that means if it was a perfect square, we check that if this square root is greater than the maximum element itself, So if it is greater than the maximum element, it cannot be present, therefore we continue. And if it is lesser, then we just check if its hash value, or basically in the new array, if its value is greater than 0. If the value at this position is greater than 0, that means candidate C was present in the original array, and hence we return true. Otherwise we return false. These are some helper methods that we used. Find max is simple. We iterate over the array and return the maximum. Fill zeros is even simpler. We iterate over the array and we fill it with zeros. Fill square values is also simple. We iterate over the original array and we get that element, and then corresponding to that index in the new array, we fill its square value. And here is the get square root if perfect method. We first calculate the square root using Java's normal function, and then we check using this condition if the square root was perfect, if the squared number was perfect square. If it was, then we return the square root, otherwise we return -1. These 4 methods are something that are very useful and very common in multiple questions, so we should be knowing them well. To summarize, we first understood the problem with example. Then we went ahead with the simplest approach. We ran 3 different loops, checked all triplets, its time complexity was big O of n cubed. Then we looked at approach 2. In this approach, we eliminated the third loop. We checked the presence of C using set. This was one of the common techniques that we will use in many problems. Here we had to use big O of n space, but our time complexity came down to big O of n square. Then we saw approach 3. Approach 3 was an optimization over first approach. Here we could see that we don't actually need to check all the triplets. We can first sort the array, we fixed C, and then we fixed A and B to the extremes of the remaining array. Then we use the meet in the middle approach to find the relevant A and B if they can satisfy the condition. That led us to a big O of n squared solution with big O of 1 space. Then we saw approach 4, where if the array size was huge, then previous 3 approaches would result in very expensive time complexity and space complexity. So we made use of repetitions by putting those only the distinct elements into a new list and then apply the same approaches on the new list. We also saw another approach where we can declare an array of maximum plus 1 and we mark the presence of the elements in the original array, and to mark the presence we just go ahead to that relevant index and fill its value with x square. Now we also saw that here we need to check the square root if it is perfect, and we saw the technique of checking that. This was a common technique where array was acting as a map and array indices were acting as a key. Then we did a code walkthrough for this same approach. This is it for this video. We'll meet again in the next video with some other problem. Thanks for watching.